Hello friends, in this video I would like to solve the following problem from the textbook Concrete Mathematics. It's problem number 67 from the 5th chapter. So we wish to find the closed form for this sum over k from k equals 0 to n of k choose 2 to n minus k choose n, where n is an positive integer. So give this problem a try, and then I will present a lemma that is extremely helpful for this problem. So the lemma, which I announced, goes like that. If L, M, N, and Q are natural numbers from 0, and if n is greater than or equal q, then the following sum over k from k equals 0 to L of L minus k choose m times q plus k choose n equals L plus q plus 1 choose m plus n plus 1. So I will prove this lemma. By the way, this lemma is also stated and proved in the textbook which I mentioned, Concrete Mathematics. By the way, it's a great textbook. It's definitely my favorite mathematics textbook about discrete mathematics. It's simply amazing. But this, as I said, this lemma is proposed. It's also proven in the textbook. I will prove it later by induction, but first let's assume for a moment that this statement is true, and let's solve our original problem. Okay, so first of all, we have k choose 2 choose 2. K choose 2 is k times k minus 1 over 2 choose 2. And again, expanding this symbol, we will get k times k minus 1 over 2 times k minus 1 over 2 minus 1 all over 2. And that's, after some simplification, it's 1/8 k minus 1 k squared minus k minus 2, and then we can simplify it further. I will write it as like that, 3 times 1 over 24, and this quadratic part can be written as k plus 1, k minus 1, k minus 2. And if you look closely, 24 is 4 factorial, and this number is simply 3 times k plus 1 choose 4. Okay, so our sum is sum over k from 0 to n of 3 can be put in front of our sum. K plus 1 choose 4, 2n minus k choose n. Okay, very nice. And maybe one more thing to be noticed. I will write our sum like that. Sum over from k equals 0 up to 2n, and I will change the order. 2n minus k choose n, k plus 1 choose 4. Okay, I have introduced a bunch of new summands, a bunch of new indices, but notice that from k equals n plus 1 up to 2n, this first symbol is 0 because upper part of this symbol is less than the lower part. from n to 1 up to 2n. So I just introduced a bunch of terms, zero terms. So it was legal. And now we can use directly our lemma, because comparing with the lemma, this part is like L, this part is like M, this part is like Q, and this part is like N. Assumptions are met, so L, M, N, and Q are natural numbers. N is greater than or equal Q, because 4 is greater than 1. So from our lemma, this entire sum becomes just 2n plus 1 plus 1 over n plus 4 plus 1, which is 3 times 2n plus 2 choose n plus 5. And this is our result. This is our closed form for our sum. It's much simpler than our sum, because, well, no sum is left. We have just 3 times a binomial coefficient. Okay, so we have solved our problem. It's great. But now the hard part is proving the lemma. So the rest of the video will be about proving the lemma which I stated. Okay, so I have written my lemma again, and I will prove it by induction, but you will see that my proof will have 2 parts. First part will be so I will use induction over variable L over L, but I have to split my proof in 2 parts. First part will be when m equals 0. Okay, in that case, we want to prove that the sum from k equals 0 to L, when m equals 0, the first symbol vanishes. It's 1 to be exact. So I have q plus k over n, choose n. It should be equal L plus q plus 1, choose n plus 1. So I have to prove that first, by induction, as I said. So first part of our induction, for L equals 0. If L equals 0, the sum is from 0 to 0, q plus k over n, which is simply q choose n. And now, because of our assumption, the assumption was that n is greater than or equal q. So this symbol is either 0 if q is greater than, is less than n, sorry, and it's 1 if q equals n. At what is the right hand side? On the right hand side we have 0 plus q plus 1 choose n plus 1, which is simply q plus 1 choose n plus 1, and it's exactly the same. It's 0 if q is less than n, and it's 1 if q equals n. So for L equals 0, our equality holds. So now let's assume that our sum that this is true for some L, which is a natural number. Now we have to write our sum from k equals 0 up to L plus 1. Let's do exactly that. Okay. Now, since our sum is from 0 to L plus 1, we can split it in two parts. First will be sum from k equals 0 up to L, q plus key over n, choose n, and the last term is q plus L plus 1, choose n. Okay? And now, by our assumption, this first sum can be replaced by L plus Q plus 1, choose N plus 1. Okay, and I will write here L plus Q plus 1, choose N. And now, by a well-known property of binomial coefficients, which is, to be honest, a definition of this binomial coefficient, we know that something like that is true. Namely, n plus 1 choose k plus 1. It's always equal n choose k plus 1 plus n choose k. And here we have exactly that, because upper indices are the same and lower differ by 1. So this sum can be replaced by L plus Q plus 2 choose n plus 2, which was exactly what was to be proven in this case. So by induction, we now know that our theorem is true for m equals 0. for m equals 0. Okay. Now, the second part of our proof. So we have concluded first part. Second part will be for m greater than or equal 1. What happens now? Again, we will use induction. So first part, if L equals 0, what happens then? Well, our sum is sum from k equals 0 up to 0 of L 0 minus k over m, choose m, times q plus key over choose n, and this sum is 0 choose m, q choose n, and since m is greater than or equal 1, this is 0. Okay, and on the right hand side, we have L plus Q plus 1, choose m plus n plus 1, L equals 0. Oh, I will write 0 here. And we have Q plus 1, m plus n plus 1. And now, let's look. We know by assumption, we know that Q is less than n, and m is greater than 1, greater than or equal 1. So most definitely, m plus n is strictly greater than q. And after adding 1 to both sides, we see that the upper index is less than the lower index. So this entire symbol is 0 as well. So we know that our that our theorem is true for L equals 0. Okay, I need some space now, so wait for a minute, because I need... Okay, we can now continue. So now let's assume that our equality is true for some L minus K over choose M, Q plus K over choose N, L plus Q plus 1, choose M plus N plus 1. For some L natural. Now we wish to expand the sum from 0 up to L plus 1 of L plus 1 minus K, choose M, Q plus K, choose N. Okay, and now I will make use again of... first let's separate our sum. So let's write it as a sum from 0 up to L plus 1 minus K, choose M, Q plus K, choose N. And the last term is for L plus 1, so it will be 0, choose M, Q plus L plus 1. I run out of space, so I will move it a little bit. Second coefficient is Q plus L plus 1, choose N. Okay. And now, because M is greater than or equal 1, this number is 0. So the last term disappears. And now we are left with sum from K equals 0 up to L. And again, I will make use of the recursion for binomial coefficients. This binomial coefficient can be replaced by L minus K choose M plus L minus K choose M minus 1 times Q plus K choose N. Very well. Very well. And now let's write this as two separate sums. And by our assumption, these two sums run through 0 to L. So by our hypothesis, by our assumption, by our inductive step, the first sum can be replaced by L plus Q plus 1 choose M plus N plus 1. And the second sum can be replaced by L plus Q plus 1 M minus 1 plus M plus 1. Why? Because of our assumption. Because we assume that this is true for every M greater than or equal 1. Because induction is on L. M can be arbitrary. Okay. And final part, again, by recursion for binomial coefficients, these two symbols have the same upper index and lower indices differ by 1. So it's L plus Q plus 1 plus 1, choose M plus N plus 1. And after changing the order, it's L plus 1 plus Q plus 1, M plus N plus 1, which closes our inductive proof, because because we assume that our theorem holds for some L. Under this assumption, we have shown that it holds also for L plus 1. So by mathematical induction, it holds in every case. So I have proven now my lemma, and before that I have solved the proposed problem, and that's it, to be honest. So one more thing before you go. Again, this textbook, Concrete Mathematics, written by great mathematicians, I highly recommend it. It's very difficult, but it's very enlightening. There are many identities involving binomial coefficients. So if you are preparing for some type of Olympiad or some contest, sometimes it's good to be familiar with lots and lots of properties of binomial coefficients. So I highly recommend checking this textbook. Okay, so that's it. Thank you for watching. I hope that you learned something. I hope that you are not entirely bored by my talking. And see you next time. Bye.